Hi, my name is Jenny Madsen from Team Integral, and we're made up of Zach Howard, Diego Juarez, Quade Murray, and myself. I'm here to introduce our thermal mug project. We are designing this mug for customers interested in buying a product capable of cooling and sustaining the temperature of their beverage. We aim to create a product that is easy to use and clean, capable of sustaining ultra-cold temperatures for longer than any mug on the market. We are learning the scientific method for the purpose of gathering accurate, reliable data applicable to our design, which is easy to replicate and may reduce future workload for others. Experiment design is aimed at defining an efficient procedure for planning experiments to obtain and analyze data which yield valid and objective conclusions. This approach gives quality information we need to deliver quality engineering work. The scientific method provides the backbone for our experimenting process. Engineering students want to dig right in and use theory and subject knowledge to tell our real-world stories on paper. We do this with math models. Experiments using the scientific method to serve to validate or disprove our hypotheses. Once our math model is validated, we can integrate our assumed theoretical values from our designs into it. This indicates whether our theoretical design is going to serve our intended purpose. With practice, this process is quite easy. Goals are defined using relevant knowledge. We then make predictions using math models and state hypotheses. Next is to plan the experiment and decide how much data is needed. An algorithm or step-by-step process should be made to define how your data will be obtained. Then analyze the data and repeat the procedure until your error has been reduced to acceptable levels. Let's explain experimenting with our thermal mug project. Our clients were interested in a container which would quickly cool down and maintain the temperature of a beverage. Our group pooled our knowledge, did some research, and made math models to predict the behavior of the temperature of water coming to equilibrium with that of a mug just pulled out of the freezer. Using laws of thermodynamics, we hypothesized that higher kinetic energy of warm water would interact with the slower frozen molecules of the barrier of glass. In the system, the energy from the warm water and cool glass would equalize and could be related by simple equation which used change in temperature. We chose to find the final temperature in our experiment because our other values could be easily measured. Our measurable values then became masses and initial temperature of the water and glass. We weighed the cup in water and measured water temperature with an Arduino temperature probe. The frozen mug was removed from the freezer to measure the initial temperature. After pouring in the water, readings were taken every 2 minutes for 15 minutes to see where the equilibrium temperature would approach. Seeing that the mug thawed very quickly, we chose to insulate the mug in a sweater for our second test run. This completed our experimentation proceedings. The data obtained from our experimentation matched closely with our predicted values from our theoretical values. This is the final iteration of the Arduino setup. Input from the temperature probe is processed and the temperature is displayed on the LCD screen, complete with units. The temperature is updated every second. Shown here is the waterproof probe we made for sensing temperature. At one end, a brass tube houses the temperature sensor. Due to its high thermal conductivity, the brass tube will allow quick and accurate measurement of the surrounding medium. One end is crimped and hot glued to ensure that it is watertight. Inserted into the other end is a plastic tube from a ballpoint pen, through which the wires are passed through. The low thermal conductivity of the plastic will prohibit the warmth of the hand wielding the probe to skew the data. It too is hot glued at both ends to keep any water from entering. Our final design will include two parts. The outer part is a vacuum flask, not unlike a thermos, which will provide an insulating layer to keep the liquid within at a stable temperature. The inner mug is made of glass and utilizes a simple twist-fit locking mechanism which secures it to the vacuum flask. The inner section can be removed easily and cleaned and placed in a freezer to chill a future beverage. When a cold beverage is desired, the two layers can be easily reunited. The cold glass will quickly chill the liquid, while the outer vacuum flask will keep it cold for a long period of time. To test the validity of the glass insert, we formed a simple math model using MATLAB. Using the thermal equilibrium equations, our tests showed that water can be chilled from 13.5 degrees Celsius to 9 degrees Celsius. The physical experimentation confirmed this, cooling the water to the predicted temperature in about 5 minutes. Let's take a moment to reflect on team strengths. We noticed that members of this team appeared to value one another's input. We placed strong emphasis on utilization of common knowledge, and obvious efforts were put into making suggested improvements from our last project, for example, being more organized. We saw that we could improve our team by coming to meetings prepared, that staying on task might have decreased the total time we spent on this project, and documenting more frequently could have helped as well. In our study of experimental design, we learned that good experimental practice involves using accurate data and not skewing our findings to fit what we thought they should be, but using the data that our experiment revealed. That feasible data is a prerequisite to solid engineering work, and that we must always be skeptical of our data. Thanks! This concludes our video presentation for My Thermal Mug project. Thank you for watching.